Yes. So linear programming problem and its mathematical form. Okay. Please read this part. A linear programming problem and its mathematical formulation. A linear programming problem is used to used in determining the optimum combination of several variables subject to certain constraints or restrictions. The linear programming problems are mathematical optimization problems with the linear objective functions and the linear constraints. So already we discussed that, right? See the way the diagram is given here. The diagram says clearly. Yes, just give me a second. Yes. So the diagram says clearly there is a linear programming which has objective function and which is set for linear equations or inequalities called constraints and restrictions. Finally, we get the maximum profit or cost. So when all this is combined, that becomes a linear programming problem. Okay, so let's see further what do we have. How to formulate. Every time we cannot formulate randomly, we need to understand the basic rules here. So please read these rules of mathematical formulation. Yes, the formulating a linear programming problem involves creation of mathematical model. This can be achieved by addressing the following question. So what is the question? First, identification of unknown variables. Generally, we take x and y for us two-dimensional linear program, right? So in general, they are taking it as x1, x2, x3, and so on for n different variables. Okay, so these are variables which are unknown. We need to identify which are unknown. For example, in the example, I gave the number of tables and number of chairs. The first examples, they were taken as x and y. They are the unknown values. By defining the objective. So what is the objective? To maximize the profit or minimize the loss or minimize the expense. Something will be there, no? So that we have to understand. So that is z. What is the z we got in the first example? That is 250x plus 75y, which was actually maximizing the profit z. Remember? Yes, maximizing the profit z. So that we have to consider with the, here 250 is a constant, 75 is a constant. In general, we have C1, X1, C2, X2, C, so on till Cn, Xn. Okay, these are the constants. C1, C2, C3 are constants, are constant coefficients, whereas X1, X2, X3 are actually variables that keeps varying. So you understand the difference between constants and variables, right? Now what we have is we have multiple constraints. So what are the constraints we have to specify? For example, the budget is a constraint. So what we had the previous example, budget was totally I can only spend how much? 50,000. So 2,500 for each chair and 500 for each table. Sorry, it was the reverse. 2,500 for a table and 500 for a chair, less than 5,000, 50,000. That was one of the constraints. So one more constraint we had was we cannot accommodate more than 60 articles. That is another thing. Similarly, we will have multiple constraints. So those multiple constraints are generalized here. A11x, A12x2, A13x3, and so on, till which is less than or equal to. Generally, it is less than or equal to. Sometimes it can even go more than or equal to. It depends upon the question. Okay, but if you have more than, there's a high chance that more than or equal to might give you unbounded solution, not the closed solution. Let's come to that later. Okay, last one, non-negative constraints. That is the variable x1 should be greater than or equal to 0, x2 should be greater than or equal to 0. In our case, the number of chairs and tables cannot be negative. It has to be either positive or 0. That's why we have x greater than or equal to 0 and y greater than or equal to 0. Okay, these are the constraints. Okay, let me repeat that again, all these things from the beginning. While formulating a mathematical linear program, so we need to keep this in consideration. First part is identify the unknown. Second part is define the objective. Okay, so third part we need to understand here is the setting the constraints. What are the constraints which are controlling our objective? Okay, or which are restricting our objective? And then non-negative constraints as well we need to keep in mind. Okay, so when you do all these things, we will end up with the proper equations. LPP in a general context that we'll understand now. A decision variables. Decision variables are denoted by x1, x2, x3 till xn. Generally, our problems will have only x and y. Very rarely we'll have z, because with the z we'll have three dimension, which we are not attempting, right? So we are only having a two dimension LPP. Remember that. Okay, so x1, x2, x3 till xn are the variables whose values are subjected to determination within the context of the problem. That's why it's called decision variable. And the objective function. An objective function is either maximize the profit, minimize the expense or loss, etc., which is again will have this in our example again and again repeating. It was 250x plus 75y. That was an example for the carpenter problem, right? And the structural constraints. So inequality is outlined as AM, XM, A2, X2, it's either less than or equal to or more than or equal to 0. They are called what? Or some number. They are called structural constraints. For example, we had x plus y less than 60 or equal to 60, and then 2500 x plus 500y was less than what? Are equal to 50,000. So those are structural constraints. It depends upon the question to question. So if you know all these things without leaving any of them, and along with the non-negative constraints, we will try to understand where is the region of uh, our solution. Sometimes what happens, it might give you only one side, or it might give you on both the sides unbounded, but most of the problems will have bounded regions like this, maybe this region, which is having all the edges. Then we have a properly, we are getting the bounded region and we can get the solution easily. But some questions will have unbounded region. So I'll come to that later. So here E says find the feasible solution and optimize the solution by looking at the corner points. Generally, we look at the corner points. If the lines are intersecting at a particular corner, so we will go for those corner points that will give you the optimized points. Okay, so let's see some examples for a better understanding. Okay, so you can check this particular chart where you can see what are the things involved in the involved as a characteristic of a linear programming problem. One is decision variable, that is x and y, objective function like z is equal to something, maximize or minimize, the constraints x greater than or equal to 0, budget, all that, non-negativity, that is x greater than or equal or y greater than or equal to 0, right? Linearity, so that's a very important part. We cannot do this for a any other degree, only the linear or linear equations are degree 1 we can do that. Okay, additivity, divisibility, all this you have to understand. And deterministic as well as finiteness. The first thing is you have to have a finite answer. That's very important. Okay, so all these are the characteristic of a linear programming problem. You cannot, if none of this is available, existing, or any of the opposite things are existing, that cannot become a linear programming problem. Okay, so let's see some example. Okay, so this particular example we already discussed, right? Let's look at the different example. So I hope this particular screen is visible for you. Yes. Can you please read the question? Second example. The first one already we did. So we are looking at the second one. A business makes two kinds of commodities, A and B. Okay. So which need silver and gold to be produced? Remember this. They are making a jewelry. The business is making a jewelry. So in type A, each unit needs 3 gram of silver and 1 gram of gold. While type B, let X be the number of grams of gold and Y be the silver in grams. Okay, so it says unit A, type A, each unit needs what? 3 gram of silver, okay, and 1 gram of gold. While in type B, each unit needs 1 gram of silver and 2 gram of gold. Okay, a maximum of 9 gram of silver and 8 gram of gold can be produced by the corporation. Okay. 9 gram of silver and 8 gram of gold can be produced by the corporation. Okay, so create an LPP to optimize the profit. So X cannot exceed. Okay, so create an LPP to optimize the profit of each type of unit A generates the profit of around 40 gram and B unit generate a profit of 50 gram. Okay, so now what is our problem is, our objective is to find the profit. So if X is the number of gold and silver, so it's telling profit should be 40 gram, uh, around $40, and each type B unit must generate a profit of about $50. Okay, so this is our profit part. We have to maximize this under these constraints. How these constraints came is, so 3 gram of gold, obviously 3 gram of silver and 1 gram of gold, it cannot exceed 9. Why 9? So where is 9? We have to understand a maximum of 9 gram of silver and 8 gram of gold can be produced by the corporation. So totally we can produce only 9 gram or 8 gram. Okay, so that's why one of the constraint is this. Another constraint is x plus 2y is less than or equal to 8. Also the positive constraints are x is greater than or equal to 0. Gold should be there. Negative is not allowed, right? So all these are constraints which are required for optimization of this function. Okay. Yes. So I'll repeat again from the beginning. If you have a confusion, what is the decision variable we have to take here? First, let me read the question again. The question says a business makes two kinds of commodities, A and B. Okay, which needs silver and gold to be produced. In type A, each unit needs 3 gram of silver and 1 gram of gold. Okay, while in type B, each unit needs 1 gram of silver and 2 gram of gold. Okay, maximum of 9 gram of silver and 8 gram of gold can be produced by the corporation. Okay, so create an LPP to optimize the profit of each type. Unit generates a profit of around $40 and B unit generate a profit of $50. So our profit should be 40 for unit A, let it be X, and 50 for unit B, let it be Y, where X is the number of units of A and Y is the number of units of B. Okay, so A cannot be a maximum 9 kg of silver, 9 gram of silver, and 8 gram of gold can be produced. Okay, that's one thing. So 9 gram of silver and 8 gram of gold can be produced. Okay, so if this is the case, what is our other condition is 3 into x, that is A, and y less than or equal to 9. So what we can do here is y has to be the unit B and x has to be unit A, and 3 times unit A and 1 time unit B has to be less than 9. So these are the constraints they have given. So negative constraint, non-negative constraint is there. So even that we are taking into consideration. Okay, so let's solve some questions clearly to understand this better. So shall we go to the questions? Yes. Yes, so what do we have here? Please read the question and try to formulate this problem. They're asking us to solve it graphically. Let's try to randomly draw the graph as well. Solve the following linear programming problem. Yes, solve the following linear programming problem graphically. The problem is here. P is equal to 70x plus 40y. Okay, which is subjected to constraints 3x plus 2y less than or equal to 9, 3x plus y less than or equal to 9, and x is greater than or equal to 0, y is greater than or equal to 0. So let me plot the graph accordingly. So there's nothing to formulate because everything is available for us. We just have to plot the graph according to the constraints given. You always get a graph in the exam. So right now I'm trying to draw a rough graph, may not be to the scale. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so now first equation is x is equal to, when x is equal to 0, what happens to y is y becomes 4.5. Okay, and when y is equal to 0, x becomes 3. So this is our one of the equation. So just trying to roughly draw this graph. So now it is less than or equal to symbol. Yes. So as it is less than or equal to, I know origin is a part of the solution. So my solution will be on this side. Clearly it is on this side. So remember this. Okay. So now we have 3x plus y greater than or equal to 0. So in this, if you put x is equal to 0, y is equal to 9. So one of the point is here, and y is equal to 0, x is equal to 3. This is again here. So our line will be again, it will be passing through the same points like this. Yes. But again, it is on the origin side only. So this is again a region. That means our feasible region is this, including this particular x greater than 0 or y greater than 0. So what are we having is, these are the points. What is our question? So our region is here. Finally, our region is here. Okay, so it is everywhere, including this. So this is our region, and we have to maximize what? 70x plus 40y. So what are the corner points? One of the corner point is, what is it? The corner points we can name them first: A, B, and C. So A is 0, comma, what is it? What, 4.5. B is 0, comma 0. C is, what is it? 4, comma 0. Our objective function is here. If we substitute, the value of z will be 70 into 0 plus 40 into 4.5. That is, we will have 180. Okay. So next, what we have is 70 into 0 plus 40 into 0, which is 0. Last one, 70 into 4 plus 40 into 0, which is actually 280. So where we have maximized is in this part. So the region of the maximized solution is optimum place is here. So that's our answer. Let's see what is the answer given here. Yes. See, our optimum solution is coming here, right? Yes. No, it is actually 3, comma 0. A small correction, please. The small correction here is, this is 3, comma 0. For our understanding, this 3, comma 0. It will become 70 into 3. It becomes 210. That is still the region of optimized solution. Okay. That is 3, comma 0. That's our solution region. Okay. That's the place where you get the highest profit. So you have to maintain that to get the maximum profit from this. So this is how we arrive at the solution for the linear program problems. Okay. So let's go to the next example quickly. Question number 2. The corner points of a feasible region of a linear programming problem are 0, comma 4. Okay, they are given the corner points already. 0, comma 4. Okay. And 8, comma 0 and 3. 20 by 3, comma 4 by 3. If the optimization point is 30x plus 24y and is the objective function, the maximum value of z. We just have to substitute, you don't have to draw any graph. So maximum value, let's see, if I put a, what happens is 30 into 0 plus 24 into 4, which is 96. Second one, b, if I substitute, z is equal to 30 into 8 plus 24 into 0, which is 240. Okay. Third one, what we have is z is equal to 30 into 20 by 3 plus 24 into 4 by 3. What happens is 3 ones are 3 tens are, right? 3 ones are 3 eights are. So what we have is 20 into 20, sorry, 200 plus 8 fours are 32. Uh, let me check this clearly. So what are the points we have here is, let us have the corner region 0, 4 corner points, B 8, 0 and C 20 by 3, 4 by 3. Our objective function is here 30x plus 24y. Okay, so is the objective function. Then the maximum value we want. So the maximum value, let's see, if you substitute A, what happens is Z is equal to 30, 0 the 0 plus 24 4s are 96. So if you substitute B, what happens is 30 into 8, correct, plus 0, which is 240. So what about the last one? 30 into 20 by 3, okay, plus 24 into 4 by 3. 3 ones are 3 eights are. 8 fours are 32. 3 ones are 3 tens are. So the answer should have been 200 plus 32, which is 232. So, but the question is minimum value, right? So the question is minimum minus maximum. We have got 232. What is our maximum now? 232. So what is our question? Maximum minus minimum. So where is minimum? We have to find out now. So what is the minimum value we have got is 96. So what is our final answer is 232 minus 96. So we will first remove 32. If you remove 32, we have 200, or we can subtract directly. So, so we'll be having what answer? 232 minus 96. So what is the answer? You can look at. Yes. So 240 is also there now. Let me do it clearly. So our question here is, our optimization function is either to maximize this or minimize this. Am I right? Yes. So first we have to understand which one will give you maximum and which one will give you minimum, and we have to subtract maximum minus minimum. That is the question here. For that we need to have the corner points. The corner points are given as, let's be A, let this be B, let this be C. Okay, yes. So when you have the Z for at A, what I get is 0 plus 24 into 4, which is 96. Z at B will be 30 into 8 plus 0, which is actually 240. Z at C will be 30 into 20 by 3 plus what we have is 24 into 4 by 3, which will give you 232. So now clearly the maximum Z is how much? 240, and the minimum Z is how much? 96. So our answer is 240 minus 96, which must be equal to 144. Definitely the answer is which one? Option D. So let's see, is it right answer? Yes, the answer is 144, which is option D, right? Yes. So let's go for the next question. Yes. Which question we are at now? Third question. So what's happening in the third question? Let's see. You operate a small factory that produces the chairs and tables. Each chair requires 3 hours of labor, and each table requires 6 hours of labor. Remember, chair needs 3 hours labor. Okay, and table requires 6 hours of labor. Okay, you have 30 hours of labor available per day. Totally, we only have how much? 30 hours labor. Okay, so each chair yields a profit of 1,000. For a chair, it is, so let us assume the number of chairs, that may be the variable be x, and number of tables be y. Okay, so first constant I can have is 3x plus 6y should be less than or equal to 30. That's the constraint we have. Okay, so you want to maximize your daily profit. So if you want to take the daily profit from the chair is how much? 1,000, and profit from the table is 2,000. That is 2,000 x 1,000x plus 2,000 y. That is our objective function. So what are the constraint? X is greater than or equal to 0 and y is greater than or equal to 0. So the objective is simply 1,000x and 2,000y. What is x and y? Number of chairs and number of tables respectively. So x is definitely greater than or equal to 0. Y is definitely greater than or equal to 0. It's a non-negative constraint. Next, what we have total hours is 30 hours. So 3 hours for a table, the chair, and 6 hours for a table should be less than or equal to 30. You cannot exceed this. These are the constraints, and this is the objective function. So let's see the answer, what they are given. Yes, same thing. 1,000x plus 2,000y is a maximization, and labor constraint, that is total labor hours, is 3x plus 6y less than or equal to 30. And then non-negativity constraint is x greater than or equal to 0, y greater than or equal to 0. If you are able to find this kind of formulate, this kind of mathematical form, then this chapter is going to be simple for you. Okay, the only thing is you need to understand the important constraints, and we have to write the equation accordingly. Okay, so let's go for the next one. Yes, so now there is a question, and we have to just choose the option. It's a multiple choice question, but see the question, it's very lengthy. Let's see, understand everything clearly. Mohan intends to allocate his entire sum of 15,000 among saving certificates and national saving bonds. Okay, the regulations stipulate that he must invest a minimum of 2,000 in saving and certificates and 2,500 in the 2,500 in the national saving bonds. The annual rate of interest as 8% for saving certificate and 10% for national saving bonds. If he chooses to invest rupees X in the saving certificate and rupees Y in the national saving certificate, the objective function of this scenario can be. So annual interest rate should be what? Annual interest rate is how much? That's what we have to maximize, right? So we have to have highest interest, right? So if X is the amount you invest in the saving scheme, okay, a saving certificate, and Y is the amount you invest in the bonds. So what happens is 8% of X plus 10% of Y, we have to maximize. Yes or no? That is our objective functions, which can be written as 8 by 100, which is 0.08x, plus 10 by 100, which is 0.1y. So which option is that? The option is here. Okay, others are not, they are all restrictions, but the objective is to have the highest interest from this, right? So that we get the highest savings. Okay, so that's the answer. So option A itself is the answer. Let's see the answer then. Yes. See, that itself is the taken to give the highest profit, or highest profit is nothing but in this case, it's the highest interest you get from the bank. Okay, so or any savings scheme. Let's go to the next question quickly. Question number 5. A company manufactures two types of product, A and B, generating a profit of rupees 2 per unit. The product of A involves 1 minute, okay, on the machine M1 and 2 minutes on the machine M2. Okay, while the product B requires 1 minute on machine M3 and 1 minute on machine M4. So machines M1 and M2 have a maximum availability of 8 hours and 10 hours respectively. Okay, so what is the question? The company produces X units of A and Y units of B. The linear constraints for this is definitely X greater than or equal to 0, Y greater than or equal to 0. That's definitely there. And then what is our other condition is A and B. So we have to have Y and X units, right? So we cannot use a machine M1 for more than 1 minute and M2 for more than 2 minutes, right? For the unit A. So that means we can have total hours available for us is how much? In a day, 8 hours. So all that we have to consider in our mind. So then what will happen here is, let me tell you, let's check the answer here, what they've done. So x plus y is less than or equal to 480 and 2x plus y is less than or equal to 600. So what is this? So 8 hours and 10 hours respectively, right? So this is hours, it is in minutes. So we have to convert 8 hours into minutes. 8 into 60, how much? 480. And what else we have is 10 into 60, how much? 600. Which option has 480 and 600? We have that here and here, but we have to look at the constraints also. So we know A needs 1 minute in M1 and 2 minutes in M2. So A needs 1 minute X plus 2 minutes Y. Okay. Which is less than or equal to 480. Right, let's formulate this question clearly. First, let me read the question first. A company manufactures two types of product, that is A and B. So let us focus on the objective clearly. So A generating a profit of 2 per unit. So they are telling X units of A and Y units of B. That means our objective is very clear now. Z is equal to 2X plus 2Y. Maximize this, right? That is our maximization. But that's not our question. They're asking our constraints. The constraints can be how much? So A can be manufactured with M1 and M2. Okay. So M1, 1 minute turn M1 and 2 minute turn M2. Okay. Whereas B requires 1 minute turn M1 and 1 minute turn. So M3 and M4, right? So machines M1 and M2 have a maximum availability of 8 hours. Okay, so very good. And then what we have is 8 hours is 480. So I want M1 and M2. So M1 is used for X, right? M2 is used for Y. Okay, so what is our constraint finally? Let's see. X plus y less than or equal to 8. What is x here? X is the units of A and y is the unit of B. Okay. So let's just check the solution later. Let's go to the next question quickly. A factory is engaged in production of two items A and B. For producing item A takes 3 hours of a machine time and 3 hours for carpenter's time. So whereas item B requires 5 hours for, let's write down these constraints first clearly. There are two items we need to produce. Item A takes 3 hours machine and then yes, 3 hours carpenter time, and whereas B needs 5 hours on the machine time and 3 hours of the carpenter time. The weekly availability of machine time is 80 hours. Machine time is 80 hours. Whereas carpenter time is how much? 50 hours. respectively. The profit earned per unit products of A and B is rupees 6 for A and 8 for B. To maximize the product, manufacturing X units of product A and Y units of product B, the constraints are okay. So what will happen here is 3x plus 5y less than or equal to how many hours? 80 hours. That's one of the constraint. Then the second one, what we have is 3x and 3y, which is less than or equal to 50 hours. That's another constraint. Okay. So, and then x is greater than or equal to 0, y is greater than or equal to 0. So, which option matches with this is option B, right? So, all of them are having more than is not correct. These two can be ruled out. Only the confusion is with these two. And in that, we have understood why. I'll tell you. First, we have to manufacture A and B, right? So our restriction is a machine hours. The machine hours totally is available for 80 hours only. And if X is the number of A units manufactured, we need 3x for A, and we can use 5x for B. So 3x plus 5y. So 5y, where y is the number of units of B produced, x is the number of units of A produced. They have a restriction of 80 hours. Similarly, 3x plus 3y for 50 hours. So, and they are going to be positive always, non-negative constraints. This is happening in which option? Option B itself, right? So this might be confusing for us. If you don't observe carefully, you might end up in giving a wrong equation. Luckily, we had only possibly option B, which is matching with our answer. So there is no confusion in this case, right? That's the answer, option B. Let's go for the next question quickly. A shopkeeper intends to buy two items, A and B, with a cost price of rupees 4 and 3, respectively. He believes that he can make a profit of 30 paise by selling A and 10 paise by selling B. Okay. His total expenditure on these items should not exceed 24 rupees. Okay, so as it is in paise, we will write it in paise only. So he is going to let A be the number of items purchased in X, and Y be the number of items of B purchased. So then what will happen here is, yeah, should not exceed 24. So 24 is one of the constraints, right? So 4x, yes, and 4 is the price of each of the item A, and 3 is the price of each of the item B, should be less than or equal to 24 rupees. That is one thing. Okay, objective function is not needed here. The constraints wise, x should be greater than or equal to 0, y should be greater than or equal to 0. So which option is that? That is option. Cost has to be always reduced, right? It has to be less than or equal to. So which is option A itself is the answer. Option B is not the answer because it is having a different value here. Whereas option C is not the answer because it is exceeding 24, and option D cannot be the answer. The only matching answer is option A here. Okay, so we are maximizing the profit, not the cost. Cost has to be always minimized. Okay, and they're asking only the constraints, but not the objective. So what is the actual objective? Maximize the profit, right? So how will you maximize the profit? By taking the profit. What is the profit here in terms of rupees? If I have to write 30 paise means 30 by 100 for X, and then 10 by 100 for Y. This has to be maximized. Maybe our value is 0.8x plus 0.1y. This is our objective function which has to be optimized. Okay, that is maximize the profit. Let's go for the next question quickly. Right? Yes. So the maximum allowable sum of the two positive integers is 5. Okay. And the maximum difference between the two times the second number, first x be the number and y be the number, maximum sum is 5. Okay, so that is the maximum allowable number. Okay, next, the maximum difference between the 2 times the second number, that is 2y, correct? And what is it? And the first number is 4. The first number is represented as x and the second number is represented as y. The mathematical expression for maximizing the product of these two numbers is, so we have to maximize the product of these two. Okay, so as which of the following will be correct? If you want to maximize them, both should be positive. So that is happening in all the options, whereas these two are happening in which option? Option C itself. That's why the answer is our option A, option C. Okay, so yes, it is option C. Obviously, option C. So we are done with the mathematical formulation. So now let us try to understand the actual approach to solve these graphs. Shall we go for that? Yes. So quickly we'll try to understand by solving some questions how to solve these linear programming problems with the graphs. Okay. Yeah. Yes. So let's first read out the information which is very important for us, and we have to follow that whenever we are solving the problems. Okay, so what is it? Yes. So here we have this graphical method of solving a linear problem. So here, what are we going to consider here is, let me check this. Yes. So these are the pointers we need to keep in mind while solving a linear programming problems with the graphs. Okay, so identify the variables of interest in the given linear programming problem. Yes, that's first thing. Create an objective function using x and y. Determine whether the goal is to maximize or minimize the objective function. Express all the constraint as a linear inequalities, because we can only deal with the linear equations or inequalities involving x and y only. Okay, so generally you keep it as x and y instead of x1, x2, x3. Okay, solve these inequalities simultaneously and highlight the shade area, and this region is known as the feasible region. If all the conditions are satisfied for a common region, that becomes a feasible region. Calculate the coordinates of all the vertices of the feasible region. Vertices nothing but what? Corner points, right? Yes. And compute the value of the objective function z is equal to ax plus by. Okay, is my audio clear to you? Yes. Okay, so yes, compute the value of the objective function z is equal to ax plus by at each of the vertex of feasible region. So, and then identify the values of x and y such that the result in the maximum or minimum value of the objective function is given. So it's maximization. Usually we look at the profit part. Minimization usually comes for expense or losses, right? This method of solving a linear programming problem is called corner point method. Okay, so let's see how can we do that with an example. Further, we have some more points to remember here. So steps involved in the corner point method. Step 1, initially feasible region is identified by yes, by graphing the given linear constraints. The corner point of a region are found by solving the inequations of the intersecting lines at each corner. Step 2, objective function z is equal to ax plus by is evaluated for each corner point by substituting the value of x and y coordinates into the expression. So that we know we already done it, right? In case one, if there is a feasible region bounded, what is the bounded? So we have a limit, right? So m and m, that is maximum and minimum, correspond to the maximum minimum value. Both will be available. In case two, if the feasible region is not bounded, for example, there is no limit, maybe it is going extending on one side of the place only. Either the maximum exists, minimum doesn't exist, or minimum exists, maximum doesn't exist. If that exists at one of the corner point. Okay, so that's what it says. Okay, so let's look at these points again quickly. Feasible region having a largest and the smallest values of m and m of the z is equal to ax plus by. That means a region which has a required point, the feasible point or objective point is called the feasible region. So feasible region can be bounded or unbounded. So bounded is one which is m is maximum and small m is minimum of value of z. Whereas unbounded is it has only one open half plane determined by either m or small m. So only one of them is obtained. If there is no common point in the half plane determined by ax plus by is greater than m and feasible region, then m is maximum value of z. Otherwise, z has no maximum value. So let's understand all this with the examples. Okay, instead of memorizing this formula. Okay, shall we go to the examples? Yes. Yes. So let's look at the question. Minimize this. We have to draw this graph and solve this question, right? Yes. Let's try to draw the graph. Yes. So let me first give the units. So let's do it quickly together, right? Yes. So what do we have here is a function 5x plus 10y. So we have to minimize this part, right? Yes. And one of the equation is x plus 2y is equal to 120. So as we have 120 and all, I'll write 20, 40, 60, 80, 100, 120, 140. That's a unit of 20, 40, 60, 80, 100, 120, 140, and so on. So second equation what we have is x plus y is greater than or equal to 60. Then x minus 2y is greater than or equal to 0. And x is greater than or equal to 0 and y is greater than or equal to 0. These are the constraints we have, right? So substituting the first constraint, when x is equal to 0, what happens is y is equal to 60. This is our first point. When y is equal to 0, x is equal to 120. This is our another point, and it is less than or equal to. So our line will be like this, passing through 0, 60 and 120, 0. Just a second. Yes, this can be the graph. So here we have the lines. Okay, our feasible region is this side, because when you substitute origin, that will be part of the solution, not this side. Okay, similarly, x plus y greater than 60. That means one of the other line will be like this. It goes to 60, 60, right? Yes. This is just give me a second. Yes. This is how it is. Okay, so it goes through 60, 0. Let me name them clearly. Okay, so now another one we have x minus 2y greater than 0. So where is x minus 2y greater than 0? X is equal to 2y. So x is equal to 2y has to go through origin, right? So if you want to know where it cuts this axis, we can substitute x plus 2y equal to 120. If x is equal to 2y, what happens is 3y is equal to 120. then y will be equal to 40. Okay, then x is equal to 80. Where is 80 and 40 is? Uh, x is equal to 2y. Yes, y is equal to 40. 40 to the 80. So it's going to be 40 and 40. This is the point where it cuts both of them. Yes, this is one line. So 40 and 40. Okay, let's come to that last point. So on this line, we have to substitute now. X plus y is equal to 60 and x is equal to 2y. So 2y plus y is equal to 60. So 3y is equal to 60. So y is equal to 20. Y is equal to 20. X will be equal to 40. 40 and 20 is here, this point. So our line goes like this. So if we have a proper graph, we will get the answer correctly. Without any hesitation, we can draw that. Right now, we are trying to approximate these values we can place. This is 20, 40. This is 40, 40. And this is 0, 60, right? Yes, this is our region. So where are our region? This is our region. So what are our points we have? Let's see, verify our answer with this. Yes, so we have got this region. The region is actually feasible region is this side. The corner points are here. I'll tell you why those region we have to take this. See, this line is below this, correct? Yes, and whereas this line is above this. And then we have to have this line x. This is the line which is going to decide x minus 2y is greater than or equal to 0. And if both are 0 minus 0, it's greater than or equal to 0. But this will happen only for this part of the line. Okay, so final our region is here. Let me show the region properly. So what are the points we have is 40, 40. So our corner points, let me name as A, B, C as well as D. So A is 40, 40. B is 20, 40. C is 60, 40, 60, 0. D is 120, 0. What is our objective? 5x minimize, right? 5x plus 10y. So where is it minimum? Let's see. So at A, what happens is 5 into 40, 200. 200 plus 40, 600. At A, the value of Z is 5 into 40, 200 plus 40 into 4, 400 is 600. At B, what happens is, yes, B is here at 20, 40, that is 5 into 20, 100, 40 into 10, 400, which is 500. At C, what happens is, we have 60, 0. So 65 is a 300 plus 0, and at D what happens is 120 into 5, which is 600. So what is our optimal point is C. This is where we can minimize our expense. So is our answer matching with this? Let's see. Yes, our answer is 60, 0. That's a feasible region. Okay. Yes. Let's go for the next question quickly, shall we? Yes. Two more questions we can solve. So determine graphically the minimum value of this objective function z is equal to 500x 400y. Okay, subject to constraints. So what are the lines we can draw first? Let's see. So we have this x plus y is equal to 200. So let's draw the graph so that we can have 200 in our graph. That is 20. I'm writing 20, 40, 60, 80, 100, 120, 140, 160, 180, and 200. Same way here also. So 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. I don't think we'll go more than that. So for one of the equation, what we have is x plus y is equal to 200. Another equation, x is equal to 20. Another equation, y is equal to 4x. Okay, and another equation is y greater than or equal to 40. So if x is equal to 20, it's always 20. So how to draw this line is, it's going to be a straight line parallel to y-axis. Okay, so it's a line parallel to y-axis. So the region is greater than 20. So this side the region will be. Next, what we have is x plus y less than or equal to 200. So that line will go through this 200 to 200. Yes, this is how it goes through, and it has to be on this side of the region. Okay, so this is the region will be. So our region is completely this side, and y is greater than or equal to 0. What about y is equal to 4x? Y is equal to 4x is when you want to solve these two equations, x plus y is equal to 200 and y is equal to 4x. We get 5x is equal to 200, x is equal to 40. So x is equal to 40, then y is equal to 160. So this is where this equation will be. So the line will be going through the origin and pass through this. Yes. And this point will be clearly 40 and 160. So our region is here. These are our corner points. Let it be A, which is 20, 0. Let this be B, which is 20, 80. And this be, yeah, this is 40, 160. And this is 200, 0, which is D. Now what we have to do is maximize or minimize. So we have to minimize, right? So where is the minimum value? ZA is 500 into 20, which is 10,000. Right. So what about ZB? 500 into 20, 10, and this cannot be minimum because it crosses the value. So ZC will also crosses the value. That will be cannot be the minimum, and ZD, which will also cross the value. So the answer is, where is the minimum value? At A, 20, 0. That's our minimum answer. Let's see. Yes, that's how we get the minimum value. So let's look at the question quickly. So Z is equal to 500 x plus 400 y. So let's draw the graph accordingly. Okay, as we want 200 in our graph, I'm going to write the units like this: 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. Okay, 20, 40, 60, 80, 100, 120, 140, 160, 180, 200. Okay, so one of the graph line is going to be like this. X plus y is equal to 200. That goes to 200 and 200 for sure. We know that, right? Similarly, another one is x is equal to 20. That's a line parallel to y-axis. Let me draw both the lines. Let's talk about the feasible region after that. Let's draw the line first. Okay. Yes, this is how it is. Next, what we have is y is equal to 4x, that goes to origin, but we have to know the points of intersection with this line also. So if you say y is equal to 4x for this line, what happens is it's going to be 5x is equal to 200, then x is equal to 40. If x is equal to 40, y is going to be 160. So with this line, it is 40 and 160, which is here. 40 and 160 should be here. Okay. Similarly, at this line, x is equal to 20, y is equal to 80, it will be here. So when you draw the line, it goes through like this. Yes. So our feasible region is very important now. Y greater than 4x. If y greater than 4x, let's see when y is equal to if y is greater than 4x, can I say 40 comma 0 will exist in this? No. 40, if that's not possible. So this side of the region is not there. So this is our feasible region. Okay, so our corner points are quickly written A, B, C. Our corner point is going to be 20 comma 80, 20 comma what is it, 40 comma 160, and on this line what we have is 20 comma 180. Yes, these are the values. So now what we have to do is we have to minimize, right? If you have to minimize, z is equal to 500 into option ZA 20 plus 400 into 80. So what we get is 10,000 plus 32,000, so which is 42,000, which is evident that should be the minimum value, because higher the values we go, this ZB will be greater than ZA, also ZC will be greater than ZD. You can verify. That means our optimal point is at A. That's a corner point we are looking at. Okay, so let's look at the values. See, that's a minimum value 42,000, right? Yes. One last question we'll solve. So what is it? Solution of the set includes which are the point that we have to find out, right? So we have to first draw the line. So if you draw the line, we'll have 2, 4, 6. Let's see the points first. So first line is x plus 2y is equal to 11. So when x is equal to 0, y is equal to 5.5. When y is equal to 0, x is equal to 11. Okay, so next one we have 3x plus 4y is equal to 30. When x is equal to 0, y is equal to 7.5. When x is equal, y is equal to 0, x is equal to 30. Okay, so we need to have 30 as well, right? So let us draw the lines like this: 2, 4, 6, 8, 10, 12, 14, yes, 16, 18, 20, 22, like this. Here 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay, it goes like this. So the problem here is we have to find out the region, right? 2x plus another equation is 2x plus 5y is equal to 30. When x is equal to 0, y is equal to 6, y is equal to 0, x is equal to 15. Okay, so what are the points we have here is, now for this particular line, we have 0, 5.5 here. Okay, and 0, 11, 0 here. One of the line goes like this. So let me write 0, 5.5, 11, 0. Next, what we have is 0, 7.5. Okay, 0, 7.5 here, and then 30, 0. It's here. So the line will be going like this. So where is the region? It is above 11. So this is x plus 2y is greater than 0. This will be going above 11. And also 3x plus y. So the region is here in the, between these two lines, right? So then we have 2x plus 5y less than or equal to 30. So 0, 6. Okay. And then 0, 50, 15, 0. It's here. So another line we are going to draw. So this line goes like this. Okay. So if these are the lines, what is our question is, our region is going to be definitely in this place then, right? So which of the following includes the point? So instead of doing all this, we can still use the points to answer the question. So let's use the point only. If x is option A, if I go for option A, 2, 3, what happens is 2 plus 3 2s are 6, greater than 8. No, it is not. So option A is ruled out. Similarly, option B, 3 plus 2 2s are 4. No, ruled out. What about option C? 3 plus 8. Yes, it is possible so far. Whereas, is it possible everywhere? 3 3s are 9. 9 plus 16. 9 plus 16 is 25. It is satisfying here. 3 2s are 6 plus 5 4s are 20. Satisfied. So all of them are positive. So answer is option C. Option C must be the answer. We don't need the graph for this. We can just observe the values and check this. Okay. Yes. The answer is clearly option C.